In our digital world, we trust locks to protect pretty much everything. Our bank accounts, our DMs, you name it. But have you ever stopped to think about where the idea for a universal digital lock even came from? Well, today we're unlocking the story of the very first one to take the world by storm, the Data Encryption Standard, or DES. Let's get into it.
So think about it. Back in the 1970s, this was the massive question facing computer scientists and governments. As everything started shifting from paper to pixels, there's this urgent, desperate need for a single, trustworthy way to keep digital information safe. It couldn't just be any old code. It had to be a global standard. And so, the race was on to create that standard. The goal was to build an encryption algorithm that anybody could use, that was reliable, and that was strong enough for both governments and businesses. This was basically setting the stage for the secure digital world we all live in today.
So where did the answer come from? Well, it came from IBM. They built on an earlier algorithm they had called Lucifer, and their new creation got picked up by the National Bureau of Standards. Now, after a really thorough and, kind of controversial review by the National Security Agency, the NSA, it was officially published in 1977. DES was born.
So what exactly is DES anyway? At its heart, it's something called a symmetric key block cipher. Okay, let's break that down. Symmetric key just means you use the exact same secret key to lock your data and to unlock it. Simple enough. And block cipher means it doesn't work letter by letter. Instead, it chops the data up into fixed-sized chunks, in this case 64-bit blocks, and encrypts one chunk at a time.
The best way to think of DES is like this highly complex, super precise encryption machine. You drop your normal, readable message, what we call plain text, in one end, you turn the crank, and out the other side comes unreadable gibberish, or ciphertext. But what is actually happening inside that machine? What you're seeing here is the whole DES process from a bird's eye view. At its core, it's really just a three-stage assembly line for making secrets. Plain text goes in, it gets shuffled, then it goes through this really complex scrambling stage, and finally it gets unshuffled before it comes out the other side as secure ciphertext.
So, first up, that 64-bit block of data goes through an initial permutation. Really, it's just a big shuffle. All the bits get rearranged in a very specific, predictable way. Then comes the main event, the enciphering, which is this intense scramble that happens over and over again, 16 times to be exact. And finally, a final permutation just reverses that initial shuffle. The real magic, the part that gives it its security, is all in that middle step.
So, what makes that 16-round scramble so powerful? Well, it's not just one lock that's being applied to your data. It's actually 16 different locks, applied one after the other. And here's the clever part. All 16 of those locks are forged from the single master key you start with.
Whoa, okay, I know this looks incredibly complicated, right? This is what's called the key generation schedule. It's the process that takes your one secret key and basically expands it into 16 unique subkeys, one for each round of encryption. Let's just simplify what's going on here.
The key idea here is just transformation. The algorithm takes your master key, it splits it in half, it rotates the pieces around, and then it mashes them back together to create the first subkey. Then it does it again, split, rotate, mash, 15 more times, creating a slightly different, totally unique subkey for every single one of those 16 rounds. Pretty cool.
All right, now we get to the main event. This is where that block of data gets put through its paces. It's scrambled and mixed and scrambled again to make it completely unrecognizable. This is the 16-round gauntlet.
16, that is the magic number in DES. The data isn't just mixed up once. Nope. It's methodically scrambled, mixed, and swapped 16 separate times. Each round builds on the one before it, adding more and more layers of complexity, making it exponentially harder to undo the process unless you have the keys.
Okay, so here's how each of those 16 rounds actually works. The data block is split into a left and a right half. The right half gets mixed with that round's unique subkey. Then, that result is combined with the left half, and to finish the round off, the two halves are swapped. This structure, which is called a Feistel network, is the absolute secret sauce. Not only does it create this tangled mess of data, but it also means, and get this, the exact same process can be used to decrypt it, you just have to run the subkeys in reverse order. It's so elegant.
Now, for decades, DES was the gold standard. It was fast, it was efficient, it was secure. But the very thing it helped create, a world of rapidly advancing computer technology, would ironically eventually be the thing that brought it down.
The security of DES all comes down to its 56-bit key. Now, what that means is that there are 2 to the power of 56 possible keys. That is over 72 quadrillion combinations. I mean, it's a ridiculously huge number. But as computing power grew exponentially thanks to Moore's law, what was once an impossibly large number, well, it became possible. An attack called brute forcing, which is literally just trying every single key, went from a crazy theoretical idea to a practical reality.
This seems like the most obvious fix in the world, right? If one lock isn't strong enough anymore, just add a second one. This idea is called double DES. You just apply the algorithm twice, each time with a different key. That should make it way, way harder to crack. But it had a hidden and pretty clever weakness.
This attack is so clever because it basically breaks the problem in half. Instead of trying to guess 2 keys at once, an attacker works from both ends toward the middle. They take the original plaintext and encrypt it with every possible first key, and they save all those results in a huge list. Then they take the final ciphertext and decrypt it with every possible second key, making a second list. All they have to do is find where those 2 lists match up. This simple trick turns one impossibly huge problem into 2 much smaller, totally manageable ones, making double DES pretty much insecure. This discovery, by the way, is what led to solutions we still see today, like triple DES.
So, by the late 90s, DES was officially put out to pasture as the main standard. But its story definitely doesn't end there. Its impact on the world of cryptography is it's hard to overstate. It really did set the stage for everything that came next.
The core concepts that made DES so effective, shuffling bits around, which we call permutation, swapping them out for other bits or substitution, and then just doing that over and over again in multiple rounds, these became the foundational principles for modern encryption. Its successor, the Advanced Encryption Standard, or AES, which protects most of our data today, is a direct descendant of the ideas that DES pioneered.
You know, the story of DES really shows us that no lock is unbreakable forever. As technology marches on, that cat-and-mouse game between code makers and code breakers just keeps going. And it leaves us with a really critical question. With things like quantum computing right around the corner, what is it going to take to crack the digital locks that protect our modern world?